आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़, की आवाज़।
Vigyan Ki Awaaz podcast series aims to popularize new ideas of science and technology, which highlight STEM, science, technology, engineering, mathematics, and medicine. This brings to the surface the efforts and researches of Indian scientists, which is desired to bring a change in community learning and teaching, access to knowledge of resources, and social paradigms. Our goal is to spread the name of indigenous Indian research stories and their masters among the masses of society in a very easy manner. Bose Institute was set up in 1917 by Sir Jagadish Chandra Bose, the founder of modern science in the Indian subcontinent. It is Asia's first modern research center devoted to interdisciplinary research and bears a century-old tradition. The institute was founded as not merely a laboratory but a temple, with its principal aims being the advancement of science and diffusion of knowledge. Swami Vivekananda, Sister Nivedita, whose influence is reflected in the institute's emblem of Vajra, was significant in the setting up of the institute, and Rabindranath Tagore were among those who had consistently inspired and supported Jagadish Chandra Bose in his endeavors. Ever since the establishment of the Department of Science and Technology, Government of India in May 1971, Bose Institute has been an autonomous grant-in-aid institution of DST. Over the last century, the institute has endlessly strived to preserve the legacy of its illustrious founder. In this podcast, we are immensely happy to present Professor Sanjay Ghosh from Bose Institute. Here, he introduces us to his experience, work, and vision.
Myself, Sanjay Ghosh. I'm working here for almost 20 years. Presently, I work in different kind of physics. One part I can say is high-energy physics, which I will try to define what it is really. And the other, I'm interested in atmospheric physics. So when we say high-energy physics, it encompasses a huge area of physics. And it actually started long back when 1897 the electron was discovered. And once the electron discovered, people actually started talking of atom, where actually electrons are there inside atom being the building blocks of matter on those days. But then subsequently things started moving, people started looking for more and more information. Rutherford did his Rutherford experiment and found that there is a nucleus which is positive charge inside the atom. And then the whole picture became complete in 1932 when neutron was discovered by Chadwick. So now there is an atom which has nucleus with proton and neutron inside and electrons outside. That's a picture of the atom. But then the experiment that Rutherford did was very simple. He had these alpha particles, which are basically ionized helium particles, has 2 proton and 2 neutrons. So those alpha particles were bombarded on helium with this thin gold foil. And these are positive particles. So if there is a positively charged center inside the atom, then it will repel it. And that's exactly what was found in the experiment. And that's the way it was decided that there is a nucleus inside. But then you see this, at this point of time, people found that there is not only proton and neutron in the market. In the market, there are n number of particles, because those days people have started working with cosmic ray. As you know, the cosmic rays are the particles which are bombarding us from the sun as well as the other galactic objects coming from them. And they found that those cosmic ray particles, they are of different nature, different kind of particles are coming in. So the question was, why do we have so many particles? I mean, if there are so many particles, then there must be some kind of internal design which sort of makes this possible for so many particles to exist. So people started working on that. In fact, we had a very strong cosmic ray group here in the Bose Institute also, which was also incidentally the first particle physics group in India under Professor D.M. Bose, who was also director of this institute. Anyway, so people in the 60s, finally, theoretically, they found that if we try to explain existence of so many particles, then we can systematize the particle just like we did in the old days, periodic table, Mendeleev. We make the Mendeleev table and we could systematize, and we can actually predict the existence of more elements. People try to systematize the particles that they have found. And they found that this is only possible if there is an internal structure. That means these are not point particles. They have something inside them. And 60s then came the era of accelerators, and people found that it is true. There are particles inside the proton and neutron, which now we know are quarks. So these quarks are now, as today, are the basic building blocks of matter, which are kind of point particles. So from there, our whole exercise of research starts. But now the question is that what are these quarks? We have seen proton-neutron. We know that proton-neutron exists and we can actually detect them. But can we detect quarks? And then came the theoretical investigation where it says, no, we will not be able to detect quarks free because they are entirely different kind of, governed by different kind of interaction compared to proton, neutrons and electrons. So that means quarks we will not be see, but we already using accelerators, we have found that quarks exist. How did we do that? And that's where comes the high energy physics concept. Why it is high energy physics? Simply because if you want to probe an object, say, for example, if you say a bag is there and you want to probe what is inside it without opening the bag, you have to put inside it something, right? You have to use probes, a pin or RP or something to inside, see something is there or not. Now, instead of that, if the object that you want to probe is smaller, then that you using has to be smaller as well. That means size has to be smaller with which you have to probe. So know the particles' existence, we have to probe it with smaller particles. Now, this smaller particle size is defined. These particles in motion are defined by or characterized by something called de Broglie wavelength. Now, that means these particles, to probe or know the existence of other particles, I have to use particles which wavelength is very small, which in turn means their energy will be very high. So that's why it is a high energy physics, because we need very high energy physics, high energy particles to actually understand what is inside those neutrons and protons. And that's what we do in general under the umbrella of high energy physics research. Now simply think about this. These particles can be there only, we can see these particles only if very high energy, which in turn you can think of very high temperature also, right? So that means if I go back in time, as we know, as of today, universe was very hot at a very early time. So that means these particles which could not see simply were there at this point of time. I mean, natural conclusion you can draw. So that means if I try to understand early universe, then I have to understand the characteristic of these particles, number one. Number two, these particles are there inside the proton and neutron, right? These quarks. If I put a lot of pressure on proton and neutron, then they will start overlapping with each other, right? That means then initially quarks were inside one proton or one neutron. Instead of that, same quark will be able to see 100 proton or 100 neutron. And that's the condition which exists in a kind of object we call compact stars or neutron stars. So that means that is another laboratory. One laboratory is early universe, where we can find these particles, seek and this effect of these particles. Another laboratory is neutron star, where we can see the effect of these particles. But again, these two are natural and we don't have any control. So what do we do in our laboratory? And in laboratory, we can see this if we can create very high hot system. How do we do that? One way to do is that you collide two nucleus. If you collide two nucleus at very high energy, then lot of energy is dumped inside and these quarks then become free within that system. That's called quark-gluon plasma. So that means if I want to understand the quarks, we can do early universe phase transition or early universe physics, we can do neutron star physics, or we can do heavy ion collision physics. And these are the three things that we do here in Bose Institute. All these three aspects we cover in Bose Institute.
Following a detailed discussion on his work, he continues to explain how the work relates to super colliders.
So you see what we need. We need to, as I said, there are two ways to understand this internal structure of protons and neutrons. We have to probe it with very high energy particles. So that's one thing we can do. We have a probe, say electron, photon of very high energy. We hit it on the nucleus and see what is inside that. The other thing is that we take two nucleus and move them. Very high energies. They come together, hit each other and dump a lot of an amount of energy. And that creates those quarks. We call it quark-gluon plasma. Now this system is transient. It is not stable. So once the system is formed, very high temperature, then this is a quark-gluon soup. Then the system will start cooling. And this quark-gluon go back to the proton, neutron and other baryons and those kind of objects. And we detect them in the detector and then we try to infer about what was the system that was formed at the very high energy. And then try to understand what is the physics of that. So that can be produced in the accelerators at very high energy, say Linear Hadron Collider at CERN. And also some other places like we are going to participate in FAIR, Facility of Antiproton Ion Research in Darmstadt, Germany, where it will be the opposite of LHC. You see, LHC, we dump a lot of energy. So temperature is very high. Here the scenario is like early universe, right? On the other hand, FAIR is the other end. It's energy is lower, stopping is very high, both the collide and stop, density is very high. That's the neutron star scenario, where temperature is high, temperature is small, density is very high, and LHC, density is small, temperature is very high. So these are the two different aspects that we are trying to understand, and both of them are through colliders. We need very high energy colliders to create such systems.
Professor Ghosh shares a deeper insight to the necessity of such work for academic enrichment as well as to broader field of human welfare.
Everybody wants to understand nature, and this is one road to understand nature. Because any system we can talk of, they are actually made up of building blocks. So if I understand the building blocks, it's difficult at this point of maybe think of first principle extrapolation. But if we understand the building blocks, a lot of things we will understand about the more complex system made up of those complex building blocks. So quest of knowledge and understanding the building blocks is one aspect. Now, what goes directly to society? That's a question we always face. It's not direct. How? But it's sort of indirectly. How? When we make an accelerator, when we try to use an accelerator, what we need? What are the things we need? We need electronics. A signal is a beam is going, hitting, coming back. So we need to detect that. So we need detectors. We need electronics, very fast electronics to detect it. You understand? So millions of particles are being produced in millisecond or nanosecond level. So we have to catch them. So that means electronics is developing. Number one. Detectors are developing. Now you will ask me why detectors are important. Detectors are important understanding because those have a direct use in medical science. Because when we talk of this proton therapy or hydrogen, these other kind of particle therapies, there we use the knowledge of those detectors, translate it to understand the human problem or human, try to treat the different kind of human disease. So that's one thing. The other aspect, which is again more of a quest for knowledge and less for direct, is the radiation effect. How the radiation affect materials, how the radiation affect human being. That again can be translated here to space technologies, because countries are trying to send people or animals outside. So we need to understand what is their radiation effect, and these experiments actually give us that idea how the radiation effect. In fact, when we make a detector, we actually very first job is to understand how the radiation is affecting this detector.
We extend our sincere thanks to Sir for sharing his knowledge and help us understand the significance of research in the field of science.